welcome to the webcast about the RCLL simulation competition on planning and execution. And I'm first going to give a run through how to run the simulation system. What you see here is essentially just the USB stick booted on a desktop machine. That is exactly the image that you can currently download. So there are two reference systems that you can run. One is based on the ICAPS rule-based engine, which is used by the team which has won the last 3 competitions. It does not use planning, but it does coordinated decision-making among the group of robots. And the second system is based on ROSplan, and that does perform actual planning, but at the current state of modeling and tooling, what we can do is we can plan for a single order, and that's what I'm going to show. So let me start with the ICAPS-based system, because that's a little easier and faster. So as you can see, I have all the commands in here already. There we go. So for one, you can use on the left just this icon, and that will essentially do what I'm doing right now, and it will automatically start the game. I will do this now step by step to give you an overview of what's actually happening when you click that button. So there's one script which runs all the different components that are required for the simulation, and that's called getSim for gazebo simulation. The arguments that you virtually always need to pass are -R to enable ROS support, -T to get ground truth about the navigation graph, -N defines the number of robots that you actually want to play. So currently I'm just playing with a single robot, and you can do 1, 2, or 3 robots. And -A means run the standard agent system, which is the ICAPS agent. So I should go to the bin directory first. So once you start this, there will be another terminal coming up, and I have to do this all over again. Okay, so that happens from time to time, that gazebo doesn't start up. That's a gazebo bug that we can't do anything about. So you will get this terminal with a couple of tabs, and I'm now going to give you a little run through of what these individual tabs are actually doing. So there we have our simulation. The first tab is gazebo. So what you will see is that it instantiates a couple of plugins and models which make up the environment. And you see the visualization to the right. Currently it's empty, and it will be filled with a random scene once we start the game. Then currently there are 2 ROS cores. The first ROS core is always the one central ROS core. If you go for the ROS API integration, that's the ROS core you will interact with. And then there's another ROS core for each single robot. So if we had started with multiple robots, you would get more ROS cores. This terminal is the referee box. That is the game controller that controls the game. The interaction with that referee box is on the next tab. That's the referee box shell. And that is what we will use shortly to run the game. Then you get a Fox tab, one for each robot that you have instantiated. So again, if you had more robots, you would see more of those tabs. And that runs all of the base software components like simulation integration, navigation, localization, and perception. Anything about this runs in here. And then the ROS integration comes on top, which we will describe a little later. And the last tab finally is the communication plugin that instantiates a proxy that the robots use to communicate with the referee box. You should not have to deal with this at all. It runs fully automatic. Okay, so how do we actually start a game now? We go to the shell terminal, and the first thing that you will do is set the team. So a team is always identified by its name. Currently there are only some examples. And there are 2 team colors. Cyan plays on the right half of the field, and magenta will play on the left half of the field. And for now we play cyan. So and then you choose the team name. Currently there's only one, and then we will add teams as based on the registration data that we got. So once the team is set, your robot should appear here. So that essentially means that the robot has reported into the referee box. And then we can start the game by pressing the space bar. So you can also see here that it shows this button, space, will start the game. It goes into the setup phase first, so we wait here. You see that the machines are now instantiated. That takes a little time. During the competition, we plan on having 1 minute of setup time that you can use. The robots are not allowed to move during this time, but if you have to do any kind of pre-computation or so, that would be the time to do this. So I'm now going to switch manually to the production phase. You see here are the descriptions of the buttons that you can press. So I'm now using F3 to set the phase, and I'm going for the production phase. So all the machines are ready now, and now the agent got the signal that the game has started, and it will actually start driving and doing the production. And you can also run without visualization. There's an extra flag for that. It's called headless mode. It's, for example, if you want to run automated games, and that's also the mode that we will use during the competition. There will be no visualization for all of the games. Okay, so the robot is now going about its job. Let me explain you what the shell shows. So here are all the machines that are available in their respective states. That is essentially also a superset of the information that you get broadcasted on the network. Then here's the basic game information, what state and phase we have, time that has passed, and points and which teams are playing. And here finally are the orders. You read this as the first thing is the order ID, then it's how many products have been delivered by either cyan or magenta, and how many products have been requested. And this is the specification, what this looks like. So there's always a base, as you probably know about the game. So this means there's a silver base, but there are no rings, and there's a black cap. And its delivery time window is from 0 to 15 minutes. And it has to be delivered to delivery gate 1. And it's marked in bold font because it's in currently active order. So you could deliver this order right now and you would score full points. The other orders will come up in the future, and you can already start working and producing for these orders, but you should only deliver those orders once the delivery time window becomes active. So as you can see here, the robot has now done the first interaction with the CAP station, and the RC meant that it was a setup for the receive CAP operation, and it had filled in from the shelf a base element with a cap, and that was now buffered, and the 1 here indicates that there's now 1 cap buffer. CAP stations can only buffer a single one, so there's either 1 or nothing. And now it's actually using the base that it got to pre-fill the ring station, and once it drops it onto the slide, it'll score the 2 points that you get for filling in material to the ring station. Okay. This particular system runs completely inside Fox, so you can look into Fox, and there's also a debug log which shows you all the CLIPS facts which have been changed and updated. That makes it easy to overview of what the system is actually doing. One other interesting aspect is this. You can get it. There we go. So you can always go to localhost 8081, that should be in the documentation, and that will give you a web interface, a look inside the robot, so to speak. 8081 is the port for the first robots, and you use 8082 and 8083 for the second and third robot if it's running. What you can see here is the most recent log messages. Every time you reload, you get the new set. And there's a blackboard that contains all the data currently stored in the robot and being processed. CLIPS, that is now specific to the agent system that's running, and that shows all the facts that the agent currently knows about. So that might be interesting if you're modeling your own system to see what the data is that our agent system has been using before. And then images are not particularly interesting because we don't generate images here for now. And in plugins, you can load and unload individual plugins, and transforms give you the transforms tree, similar to what you can see in ROS. But I think the most interesting part is this Clips view. Okay, so much for the Clips view. I'm now going to shut this down just by closing this terminal, and that will close down the full simulation. Any questions so far regarding this part?
So I had one. Okay, maybe I'll have to come back later.
Okay, that's
That question.
Okay, so the second thing that we're doing now is essentially to do the same thing again, but instead of using the Clip-based agent, we're now going for the ROS plan system. And that's probably the way of integration that more teams will be doing. How that works is that the base system that was running before is exactly the same, but there's a complete ROS integration, meaning that you can communicate to the referee box completely through ROS, and you can also interact with the robots completely through ROS. And that's all mapped onto the central ROS core. So let me run this. Okay, so I can move this. We're going to do this manually. So the difference now is the basic arguments are the same again. So we run a single robot. We want ground truth about the nav graph, what the positions of the machines essentially. We want the ROS integration, obviously. And additionally, we also set a launch file that we want to launch on the main central ROS core. That's why it's ROS launch main. And here we use the launch file that we provide in the RCLL ROS package. And we use the one for the full production of a single robot, including the RQT visualization. And that is relevant, as you will see in a minute. So let me start this. Okay, so it runs the simulation again. At least it should. There is a simulation. Okay, the world is empty again because we're going to generate a new one. Here's the central ROS core, just as before. Now there's another tab that is the launch file, which was started, and I can go through a few of the details soon. The same ROS core as before, the referee box, the shell, the Fox instance, which now does not run the Clips integration, but everything else is the same, and the communication instance, which is again the same. So you're going to need to set the team name. And again, now our beacon signal is sent and the robot appears, and this is what happens here. So here first we got an announcement that it could not send the beacon signal because the private peer was not set up. And then once I set the team name, it could actually identify itself and then set up the private peer and started announcing itself, and also detected the referee box on the network. So, and that's when it all appears here. So now let me start the game again. It's now in setup phase, so we again wait for all the machines to be instantiated. As you will notice, that the machines are always positioned differently. So it's randomized, the setup. That's actually not a very pleasing setup, but that can happen. So now I'm going to the production phase again. Now the referee box will start broadcasting information about the game. It will broadcast the orders, the machines, and this is now mirrored into the knowledge base of ROSplan. So as you can see, that here it started adding machine information. It set the machine information once it received it. First, it started adding orders and the properties of these orders, and this is what you can see here. So that's the ROSplan, RQT ROSplan dispatcher view. And here in the fact base, you can actually see, so there are some facts which are in the problem file or in the initial situation file, which is always loaded. So there's a specific module which is run on start that initiates the basic view. And then you can see here later on the dynamically asserted functions. So there are a couple of nodes which listen to information from the referee box and translate this into content of the ROS plan knowledge base, like order information, NPS state information, ring specifications, which is all dynamically announced only during the game, which you cannot know beforehand. Okay, so we also in the initial setup set a single goal so that we want to fulfill the standing order 01, and you can change it at any time, of course. And now we need to actually initiate planning, and then it calls out to ROS plan to generate the plan. And as you can see already, the plan for the very simple product is rather involved, and it's now starting to run the actions that are required. So if we go to the simulation again, you can see that the robot is moving and doing its job. So the first thing that it needed to do was it needs to go to the base station to get a base here. Actually, that's just something that it's doing in the beginning. So you see here that the plan that it creates is not optimal. And what it actually wants to do first is here to get a cap carrier with the gray cap from the cap station. And then it will prepare the cap station for retrieval and then put the carrier into the machine for buffering. So that's also the same that the Eclipse agent had been doing before, as we saw. And as you see here in the background, that's the Astral executive running of ROS plan to call out to these actions. Are there any questions so far about this?
So let me just add, right, that basically you can use, if you want to, right, you can just use this system and replace the planner that ROS plan calls with your own planner, and that's it. That's enough to participate. Of course, you can do more, but you don't have to.
And then the same goes for the model. So you might use the same planner or a different planner and your own custom model. I mean, that's only configuration of the ROS plan system. So that would be a very minimalistic approach to make changes to participate. So the barrier should be rather low.
So I think I had a question about the ring station.
Mm-hmm.
So you said before the robot was bringing a base there that it would later use as material.
Mm-hmm.
So do I have to tell the ring station beforehand that I want to, what kind of ring I want, and then bring the material, or can I bring material and store it there?
You can bring material at any time in the game. There's also no specific preparation that you need to do to fill in additional material. You can do that at any point in time. The only constraint being is that it can buffer no more than 3 additional materials.
Mm-hmm.
So if you have 3 in there, then you first need to produce a ring which requires at least one of those.
Okay.
Okay. What I would suggest now is that we maybe briefly go over the launch files so that you get an impression of the nodes which are running.
Yeah, that would be great.
So here, so you saw that it's in the RCI ROS package. There are all the launch files, and the launch files we've been using is this RQT file. I'm not going to talk about this because that essentially only includes the one without RQT and SRQT. So that's not particularly interesting, so I'm going to use this one. Okay. That should be easier to read. So the first thing that we have up here is the basic simulation integration, which is provided by the RCLL Fox Sim package. And we can go into this a little later, but what that essentially does is that it runs the nodes which communicate with the basic simulation through Fox. This should be here, Fox launch. Okay, so it launches the ref peer integration, so that is responsible for communicating with the ref box, and that's the basic simulation integration. And that's there we go. And yeah, so there's not much to it. One specificity here is that this also runs the beacon signal. The original idea behind the beacon signal, that is the message that you periodically send to the referee box so that you appear in the referee box. The idea there was that the executive or the planner or whatever is running the system would send this periodically. So if you go for a custom executive or system, the idea would be that you start sending the beacon signal in a 2-second interval and then remove this node. And then another thing here is the skill integration that allows for skill. Okay, let's go back.
So basically, even if I launch everything in ROS mode with ROS plan, then Fox is still doing all the heavy lifting, right?
That's true, yeah.
Okay.
So here's the domain file. That would be also something you would probably like to change if you change the planner. Because PopF is not very expressive in its feature set of PDDL that it supports. Then there's the knowledge base of ROSPlan that stores all the information, the facts that we provide about the game. That is stored in MongoDB. The next part deals with this. And then comes the ROSPlan planning system, and there are some special things. This is basic configuration that can always stay the same. The interesting part is here. So there is where you can replace the planner command with your own command. So currently it's using PopF, the version that comes with ROSPlan precompiled. And this is an argument for the dispatcher that says try redispatching an action at most twice and afterwards give up. The version that is currently not commented out here, so that's currently used, is one that uses PopF's one-shot solving, meaning that it only goes for the first solution it can find and then uses that. The other version that is right above here, this one, that will actually set a timeout of 30 seconds, run PopF in its anytime version, and then PopF will try to optimize the plan, the initial plan that it found for 30 seconds. The benefit is that you might get better plans. The drawback is that it will always use the maximum time that you set here. So even if it finds a plan after 10 seconds, it will continue trying to optimize for 30 seconds until the timeout hits.
So that's the total planning time.
Yes.
Okay.
So, I don't know, this probably took 10 seconds or something. Open the log later, but it does not work anymore in that short amount of time if we go for more complex orders, more robots, or more orders at the same time. We're really going for the low-hanging fruit in this demonstration. So the next is a parameterization of the actions, or a mapping of the PDDL operators to skills that you can actually call in the behavior engine. And we will look into this in a little more detail later on, because that's actually important, because you probably also need to treat this if you have custom ops and a custom model that you use. if you use ROSPlan for execution, it's important to note that ROSPlan does not by itself take care of asserting the effects of actions after an action has been successfully executed. So the action execution or the action interface needs to take care of that. And we do this, but now comes a conflict that some of those effects that you have are relevant at planning time, but you're actually getting them dynamically from the system at execution time. And that is why we have these ignored effect predicates. One example is, I think, the MPS state. That is not modified, but read from the system, and that's why it's an ignored effect predicate. But if you had, for example, a prepare action, then you would actually have to model that you changed the state of the machine. Okay. The robot identifier. So we dispatch all our actions to separate components for each robot, and we assume that the PDDL operators that are executed have a specific variable that identifies which robot is supposed to execute that action. And this is what you specify here. So you say that the robot identifier variable name is R and its type is robot. And then the action execution can match on this, as we will see later in the parameterization of the node, to know when to take care of an action and when to ignore it.
So basically the robot string here should correspond to the robot type in the PDDL domain, right?
Exactly. Then we have a couple of ROSPlan interfaces which do or provide to ROSPlan the actions that you can execute in the environment. One is ROSPlan Interface Behavior Engine. That is responsible for skill execution. And here, and that is where the robot identifier comes into play again. So if you have more robots, you would have multiple instances of this ROSPlan Interface Behavior Engine. And this will be parameterized in two ways. One is you map or remap into a sub namespace depending on the robot. And in our setup, you would always have namespaces robot 1, robot 2, or robot 3, depending on the number of robots. And here's the robot identifier variable again. So that is the value that this specific node instance expects for the variable name of the operator, of the PDDL operator, to take care of the action. In the 3-robot version, where you have 3 of those instances, they would differ in the namespace they apply to and in the variable value that they expect for the robot identifier variable.
Mm-hmm.
The next part is the integration with the RCL referee box. There's one integration with the referee box for each robot, but it does not matter which robot actually sends commands. So what we do here is that we remap the prepare machine service, in that case, to the first robot's prepare machine, and that will always be the same. Since we assume that the robots will be up all the time, in installation they are, we can do it. And then there's some parameterization. I think it's rather static. It's mostly maps. Oh, well, no, it's actually not. Okay, let me show you. So what this does is it describes what the node needs to update on the side of ROSPlan in terms of variables and predicates. So here the first part means which op names to expect for the different prepare operations of the machine. So if you were to choose a different name for your operator to prepare a base station, this is what you would need to change, so that it could actually recognize the action that you call. Then, for the base station preparation, we need to know how to interpret the arguments, and then again, these are the values that you will pass on as arguments to the prepare base station operator. So what we need to know is there needs to be one variable that identifies which side of the base station the base should be delivered on, and then which color you're interested in. And in our domain, these are called side and DC for base color. And then we need to know how to interpret the values that we get. And then if you choose any different naming for the values or for the arguments, this is where you need to change those. And the same goes for the other prepare operations. And there is one concept which is called the succeed actions. And this applies in particular here. So in our domain, we have a BS dispense operation which models that the base station has now dispensed the base we are interested in. It's essentially the reaction to our operating the machine. But there's no actual action that we need to take. So we define it as a succeed action, which just means that the action is always assumed to have completed, and we take care of asserting or retracting the appropriate effects. Let's go back. Are any questions so far for the RefBox integration? Okay. So now,
wait, maybe I have one.
Yeah.
So basically this assumes that the domain and the execution has like a one-to-one mapping between the actions, right? So if I want to prepare the base station and then take the base that comes out of it, then I need to send basically two actions. And I need to have two actions in my domain for that, right?
You can have only one. So I mean the prepare is the action which has an effect on the simulation, so on the real world, so to speak. So that you need to call. So that is where we just need to know the mapping of the action name and the action arguments. You can have more arguments, but you cannot have less. For the dispense, that is just specific to our modeling. If you do not have that, well, just ignore it or don't add it to the succeed actions. We don't care. If you had in your model more than one action that you need to execute, you can also add more succeed actions.
Oh,
it's
okay.
just to give you tool support to have these actions which you want to succeed in that way and for which you want to have the proper effects being applied to your knowledge base.
Okay.
Okay.
But basically, right, the core of the domain is going to be the actions that the simulator can execute, which is basically robots driving around between positions and picking up or putting workpieces somewhere, or sending commands to the machines, right? So we don't expect that to change, drastically. But of course, the details can change.
Yeah, so maybe I have to think about it. Maybe it makes more sense to, I don't know, have some actions represented different in the domain than what we want to, so basically different from the skills we want to call. But yeah.
Yeah, no, so it's possible, right? Especially if you modify the ROS-plan interface, right? So you can have, for example, a high-level PDDL action, which the ROS-plan interface breaks down into a set of skills that are executed one after the other, or whatever. That's definitely possible. It would require a bit more work, but you can do that.
You can add your own interfaces.
Yes.
And the way this works is that ROS-plan has a topic on which it announces all actions which have to be executed, and then all the nodes, all your interface nodes need to listen for that topic and decide whether they are responsible for this action or not. And you just make sure that there's no overlap between separate nodes, that two nodes start operating on the same action, for example.
Yeah, makes sense.
Okay, then we have our little state estimation of the domain. Currently, that's a translation of the machine info and the order info that we receive from the referee box and post the appropriate fact updates to the ROS plan knowledge base. And again, there's this remapping of the topics which are relevant to us to the Robot1 namespace, and then a parameterization, and works in a very similar way to the refbox file that I just showed you, that describes what predicates it needs to update for machine info or order info. So if we briefly look into this. So here it also creates instances for all the MPSs which exist, so you don't need to pre-specify. And yeah, here's a very simple example. So the MPS type predicate, and we make certain assumptions, essentially that it requires two arguments, and the one is the type, and the other one, the one is the machine name, and the other one is the type of the machine. So, and then you can define the predicate name, but it needs to be a binary predicate, otherwise it won't work. And further down below, you can actually specify the name argument, what this would be called, and the type argument, what this would be called, and the actual values that we can set on this. The names are fixed because they are kind of standardized in the leak. So we go with the standard names to avoid confusion. We don't allow to overwrite this. But for the type value, you can overwrite if you want to. So, and here's an example. In our domain, it looks like this. So we have an MPS type with an MPS and a type name parameter called MNT. And the later specification describes that predicate. And this is something that we would essentially assert about the MPS type if it was not already in the fact base. So when we start initially, we get the first information about the machine, we will check the knowledge base if it contains any representatives already, and if not, it will assert those. And if they would change, it would also update it, but for the MPS type, it's obviously not going to change. But for the MPS state, it might very well change. So here's an example that there could be a machine which is idle and then becomes prepared, and then we would do the update of the MPS state fact, retracting the old fact and asserting the new one. And that is also why we have the MPS state in the ignore effect predicates, because we do not want the actions, even though they modify the MPS state in their effect, to actually modify the fact base, but we want to retrieve this from the actual simulation. And the reason there is to use this for error detection, so if the state is not what you wanted, but during planning time, you need to have this effect in here.
Yep.
For okay. And very similar for the order info, so I'm not going into detail about this. And then we have an additional node that's just a convenience node. It's just describes the initial situation, and it says it describes the instances and effects, instances and predicates that you want to assert at the start of the game. So there's an argument saying that we want to clear the knowledge base completely, otherwise it would be additive what you have in there. And you can also trigger planning immediately, which you might want to do during development time and debugging, but not for the actual game. So this looks like this. So we first describe all the objects that we have statically in our environment, and then the initial predicates. How this works is that the key in this. The MPS type here is the identifier of the predicate, and then there's a list of lists. The outer list gives the separate predicate instances that we need to assert, and the inner list gives the arguments that we need to pass to the predicate. So here we don't care about the types, we just assume that these will be correct when asserting, so it's your duty during the definition. Yeah, and the only assumption that we make is that the lists here are of the proper arity given the predicate specification in the domain file. And then we describe all the initial stuff. And then in the end, you can also specify a goal. So that is the goal that you saw here in RQT as order fulfilled. This comes from this initial situation. Okay, direction actually failed, so probably the machine was standing wrong. Okay, we can look at this. So, okay, and that concludes the basic launch file. Any questions about this? Any further questions?
Not at the moment.
Okay. So,
Then maybe we should take a look at the PDDL domain file quickly.
Okay. So that's also in the RCL ROS. Essentially, RCL ROS hosts all of the configuration launch files, domain, all the non-code stuff. So we go for the production domain. Basic types, robot team color. I'm not going through all of those. I don't think there are any. Consider a couple of. You were going to say something?
No, I think it's mostly self-explanatory, but maybe we should kind of take a look at the predicates and actions briefly.
So, and yes, so this also rather classic.
Okay, so one thing about the location, right? So you've got the predicate at, robot, location, inside, right? So basically the location is which machine the robot is at, and the side is the input side or the output side. And both of these together define a location. So the nav graph, right, has a node for each machine side, not just for each machine. So that's important to keep in mind, that just saying it's at machine base station, right, is not enough. You need to say which side the robot is at.
And that's also relevant for driving to a machine. So you cannot just say drive to the machine, but you always need to specify the side of the machine you want to be at.
Yeah. And then, so you've got holding and can hold, which is kind of just a gripper standard thing.
We have the dual because that's a domain for POPF, which cannot do negated preconditions.
Yeah. So, right, so you've got some specifications of the machines and the machine states, which is all the MPS type, MPS state, BS, RSCS, and so on. The predicates that start with order define your goals. So you've got an object of type order, and then order complexity, base color, ring 1, 2, 3 colors, cap color, and gate define the order. Right, it's the structure and fulfilled, so whether it's fulfilled or not. And then
order info knowledge base updater.
And then the and then the WP predicates, right? WP base, ring 1, 2, 3, cap, and so on, define what each workpiece currently has.
Mm-hmm.
And then there's a bit of a hack here, which is kind of a special action which matches a workpiece to an order. So I think it's at the end, right, Tim? Can you maybe go there?
actually only at the very end in the
Right.
fulfill order.
So you've got the fulfill order actions, right? And that basically, I mean, the important part is it takes an order and a work piece, and it makes sure that the work piece matches the order. So that's how you match these two up. Another thing is that we only have partial support in this in Rosplan basically for order delivery windows. So we have functions which give you for each order the delivery window beginning and end times, which are absolute times. But since there's currently no way to add a timed initial literal to the initial state in Rosplan, then it's not fully integrated.
Mm-hmm.
And I mean, yeah, I think the other actions are fairly self-explanatory, right? You can send commands to the machines, or you can send commands to the robots, basically.
And then we have this modeling helper actions like this BS dispense, which are these succeed actions that we only need to have proper updates to the world model during planning, but which do not actually have an effect on the environment during execution.
Mm-hmm.
There's moving the robot somewhere, entering the field. Discarding a workpiece just means dropping the workpiece. Getting something from the shelf or getting something from the conveyor belt are two different actions. Putting something on the conveyor belt and putting something on the shelf. And these in particular are the ones that are relevant when it comes to execution through the behavior engine. And for this, I want to show you the action. So the action mapping describes to the behavior engine interface node what to execute for specific operators from the domain. Mm-hmm. So let's go for a simple one here. So how this works is that you specify as key the name of the operator on the PDL side, and the remainder or the value describes the string, skill string that's executed. And here you can do pattern replacement. So anything that starts with a question mark, opening parentheses, and closing parentheses, defines an argument taken from the PDDL operator when it's called for execution. Mm-hmm. And in between, you give the name of the parameter. So there may be more parameters, but you can also choose to ignore those on this side. And then there's a modifier, and the available modifiers are keeping as is as a string, which means that it gets quotation marks. You see an example down here. So there we just say the team color that we get should be encoded as a string, and that wraps it in properly in quotation marks before execution. Then we have a Y for symbol, which means just print the symbol but don't do anything else. And we use that here because we add a suffix -i here for the input side. Y and S can be lower and uppercase. Lowercase means take as it's presented from Rosplan, which in the case of using popf as a planner is always all lowercase. Mm-hmm. And using the uppercase modifier, uppercase Y or uppercase S means convert the value that you get to an uppercase string. And here we choose to do that because it's essentially a constant name which in our domain model is uppercase and which we need to pass on uppercase, but which popf converts to lowercase, unfortunately. There's another feature that you can use if just having the arguments is not sufficient, but you need to modify the value, and you can actually use this chaining description here. So that means here, starting from here, there's a substitution. I take the argument toSide, so that's the name, and then type this to a regular expression. So, and then comes the regular expression. What I want to do here is, if toSide is input, I want to replace it with -i. And then there's another, so, and after this application of the regular expression, we apply the next regular expression. Because they're exclusive here, it's essentially an either or. And then you can again pass a modifier in the end. There's only a limited subset of regular expressions which are possible here. In particular, you cannot use parentheses or slashes, not even escaped in the expression. And the matching is always performed ignorant to the case of the argument. Whether it's lowercase or uppercase, for the matching part, your input, we actually don't care.
Okay. So I guess all the expressions that I can use are listed up there?
Yeah.
Someone? Yeah. Okay.
So there's extensive documentation above about what I said. So there's also something about integers and float values. Should you care or should you have those? But no. So there's, for example, also one example down here. So that would mean here, what you want to do when the robot enters the field, there is an argument to the skill that allows you to wait for some time before entering the field. And if you had parallel execution, true parallel execution, you might want to have all the robots wait for a different increasing time. Mm-hmm. And here we actually do that by reacting to the R parameter, which is the robot name. And if it's R1, replace it by 0. If it's R2, replace it by 3. And if it's R3, replace it by 6 seconds. And choose and then pass this on as a float value. So that there you can see this is kind of a switch case based on the symbolic argument, generate other arguments. Okay. Any questions? Action mapping?
No, not right now. I think I have to look at it in detail.
Yeah, so the available basic skills and example operators for these are all described in the manual. Mm-hmm. So the rules and regulations, which in the second part has technical documentation about integrating simulation, and that includes all the skills which are relevant. There are even more skills than that, but you probably will need only this subset.
Yeah.
Okay.
So I think we covered most of the important parts, at least to get started, right?
Mm-hmm.
So is there any component that you think that you want to ask about, Andreas?
Yes, maybe on the hardware side. Tim, you said something about specific USB sticks. Maybe you can post a link to them, because I had trouble with my own USB stick. It was too slow.
Yeah,
So
I can. Yeah, I will send what we have been using and which works fine, and then we can try to get those or similar ones.
And by the way, you can just run this in a virtual machine.
Yeah, I had difficulties with each approach so far. So the USB stick, okay, that's probably due to my slow USB stick. So in the virtual machine, I didn't manage to get hardware acceleration, which I guess is necessary if you want to run Gazebo, right?
Yeah, only necessary if you want to run this visualization. You can run.
Yeah, I've been running my virtual machine without hardware graphics support, or at least accelerated 3D graphics, and it's fine. I mean, it's a bit laggy, but that doesn't really matter.
So it doesn't affect like the simulation. It's just the visual then that is lagging, right?
Yeah.
Okay, yeah, well that also worked then.
So what you can do is run headless in the virtual machine and then run the Gazebo client from the outside.
Oh, okay. Yeah, that would also be a good approach.
Yeah.
Okay.
Right.
So when I tried to run from USB stick, I also noticed you can update the USB stick.
Yes.
Are there like, yeah, do we expect regular updates or is it only for emergency cases?
So whenever we post it, we will post an update. You can also use the update if we push anything to our RCLL repositories, ROS repositories. They will be automatically pulled and built on your system when you do a SimStick update. And if there are patches that we need to the Fox integration or the simulation because something didn't work, then you will also get these through SimStick update.
Okay.
But we don't expect, regular updates. We expect a few bug fixes and, maybe one or two changes for kind of defining exactly how you're going to run the competition. But we don't expect this to change drastically, except for adding support for another executive from MIT, which will happen hopefully very soon.
Yes,
No,
if
I've
there
been
were
trying to install it natively on Ubuntu, and I had trouble with that. So
Yes.
and also the update script wasn't working.
Yes,
So
running this natively on Ubuntu is between hard and impossible.
okay.
I tried that as well.
Yeah, so
but
that's
what you can do actually, because ROS is a distributed system, you can run the simulation from the SimStick image, right, on a Fedora OS, and then you can run all of your stuff on another computer running Ubuntu, and it just has the Fedora computer as the ROS master. So that actually works. I tried that with 2 different VMs.
Okay.
as long as you use Kinetic on your Ubuntu.
Yeah, sure.
Yeah. All right. So I think we'll stop here. And of course, if you have any more questions, then we have our Google group, and you can post questions there, or just send us emails. And we'll try to help as much as we can.
Okay, great.
Thanks for attending.
All right.
Sure. So,
Bye-bye.
yeah, have a nice evening.
So good luck to us all.